any questions from last time? Okay, so, let me recall for you. The last thing is we finished up this business about, any overring of a one-dimensional Noetherian plane is still, Noetherian and one-dimensional as long as it's not the quotient field. Right, not written down what I wanted to. We say that, the integral domain is an almost Dedekind domain. If our localized P is an Noetherian valuation domain for all P. All primitives. Now notice this condition, I have four conditions, for Dedekind. And I forget whether it's the second, I think it's the third condition that I had for Dedekind. This is very similar to this. Do you know what the missing thing is?
Well, the ring itself is not a Noetherian.
That's right. So in the condition that we had for Dedekind domains, it was exactly like this, except for the fact that we assumed that the ring was Noetherian in the first place. And we pointed out, I'll show you really quickly again, that just because every localization is Noetherian doesn't mean that the original one was Noetherian. So, of course, any Dedekind domain is almost Dedekind. Otherwise, that is a terrible, terrible choice of terminology, right? Any Noetherian Dedekind domain is almost Dedekind. So here's a couple of notes. Almost Dedekind. Of course, this might be a little bit less than satisfying because it's also true that proofer plus Noetherian is equal to Dedekind.
Almost Dedekind is a proofer.
But what's that?
Almost Dedekind is a proofer.
Almost Dedekind is automatically proofer. That's right. And so almost Dedekind is stronger in proofer than proofer in that sense, because almost Dedekind are small proofer. You can't stack the primes too high. And this actually follows right here, right, from this here. So let me give you the following theorem, which I will not prove, but I will sort of coach you on a couple of those. But let me be a domain, not a field. We'll see if I can remember why I put that in there. I'm probably avoiding some triviality here. The following conditions are equivalent. One, D is almost Dedekind. Two, this is one of my favorite things about almost Dedekind. Cancellation holds for non-zero ideals. And let me be specific about what I mean. If I zero ideal and IA equals IB, then. So it's cancellation, like you can't say ideal. Notice that, well, I'll notice that. Three, D is a one-dimensional proof for domain. Can I stop there? Ooh, some more words need to come out of my mouth. That's what everybody loves to hear. Jim's gotta talk more. So can anybody give me an example of one-dimensional proof domain that's not almost dedicated?
Valuation domain with value group R, like real numbers.
If you have a one-dimensional valuation domain, for example, that does not have value group Z, then, so I need something else. So given your example, you want to take a shot at what else I can throw in here? Uh, No one item hope match my deal. Right, so in other words, so you can't square a maximal ideal and return the same thing. You can do this for valuation domains that have a value group like Q or R or something like this. So if M is in max spec R, or D, I guess we'll call it here, then M squared is strictly contained in M. So you actually go down when you do that. And number 4, D is proofer and intersection of AN is equal to 0 for all ideals. A is strictly contained in B. So all of these conditions are equivalent, and they mean that your domain is almost Dedekind. Notice these 3 and 4 spin-offs of proofer. You can either say, okay, you got a tiny proofer domain, it's one-dimensional, you can't stack the prime ideal very high, and none of the maximal ideals are idempotent. Or you can say D is proofer without that condition here, and when you intersect any ideal, or I should say, when you intersect powers of any ideal, you get to 0 ideal, which is, this is what I kind of expect to happen in most of the behavior range. Notice, for example, if D is Dedekind, then all these are satisfied, right? And in particular, notice this cancellation property. This works very easily in Dedekind domains, doesn't it? Because all you got to do is hit the left-hand side by the inverse of I, right? I inverse. And so the interesting thing about this is I would suppose that in an almost Dedekind domain that is not Dedekind, you might have these really badly behaved ideals that are not finitely generated, because otherwise, if all the ideals were finitely generated, it would be Dedekind. But even those bad ideals in this domain cancel. You don't need an inverse, they just cancel. Here's an example, and I've gone through this before, so I won't beat this dead horse into even worse situations. But so what you have is start with Z localized it to say something really easy like this. Z localized at two has a unique prime. Well, let me rephrase. Z localized at two has a unique non-zero prime, namely two. You can take a quadratic extension of this, where this splits into two primes. So now you're taking two, and, two different primes, right? So I don't want to join the square root of two, but I join a quadratic extension where this splits into two distinct, co-maximal primes. There's a famous theorem in Gilmer's book that this can be done. And then keep iterating the process. At this level, I'll split this into two primes, probably Q2, I guess. And just keep doing this tree. Notice at every point, what you have is a principal ideal domain with only finitely many primes. Here you've got one, here you've got two. At this level, right, at R1, you've got these two. At R2, you've got these three, because notice you left Q1 alone. At R3, you've got these five, because you split this one, but you left these two primes and so forth and so on. And notice that if R is basically what you're doing, you're taking quadratic extensions in every step. So here's what we know so far. If you take the union of these quotient fields, it's going to be an algebraic extension of Q, right? And so immediately you know that this construction has to be proofer, right? Every element in here is integral over Z localized at two. And so it's got to be one dimensional. And there's only one maximal ideal. It's easy to check, in fact, that M is the only maximal ideal. And we've seen before that what happens when you localize. Well, notice that what you get in this construction that we've had, let me do more than just draw a picture of it, is you have the two factors in the first step of P1, Q1, and then P1 factors in Q2, Q2, and P2 factors into Q3, Q3, etc. If you localize at this maximal ideal here, what happens is all these Q's all the way up turn into units. So now what you get is 2 is associated P1, P1 is associated to P2, P2 is associated to P3, and so forth. So what you've done essentially is you've made like Lawrence Welk here and squeeze the accordion, and all these primes are just the same thing. And so again, what do we have? It's one dimensional because it's integral, it's an integral extension, it's proofer, and maximal ideal is in fact principal. So M squared is properly contained in M since it's principal maximal ideal. Okay, any questions on that? Okay, so I'm going to talk a little bit more about Dedekind domains. I'm going to give you some details about some of the behavior and some sort of number theoretic examples to show why people would care about this. Let me recall a couple of facts. I'm going to recall a few facts from this. Uh, so suppose I've got the proper ideal. Non-zero is the important part. That's that. This is one of my favorite, we're gonna use this in a group of something we do in a moment. Notice if I is vertical. Then choose A. And here we have I inverse, is equal to AR. And there we go. On the other hand, if you have that I times J is principal. Then I'll give you the answer and I'll let you verify it, yourself. Then I inverse is equal to A inverse J. That's easy to. Okay, let me kind of go over sort of a baby example. I'm gonna build on this example later, but I think it might, help in the flow to talk about this. Recall, we have shown that if then we have shown this before, and we've reworked this to get different principal ideal factorizations to kind of try to explain why this thing, although it has unique factorization in prime ideals, because it's Dedekind, it doesn't have unique factorization in the elements. Let's see. So you can use this factorization to rearrange but you can also do this. Let me see if I did this, my nose becomes correct, it's positive. Um. And I forget which order these two go in, whether this corresponds to this one or this one, but you can figure that out. Now, here's one of the things that's gonna help us talk about, for example, factorizations among other things. Class group. Also recall. Probably. Class group was, you take the group of invertible ideals, which in the Dedekind domains, for Dedekind domains, the invertible fractional ideals form a group, with the inverse of I being I inverse, the identity being R. The principal non-zero ideals form a subgroup. Well, let me just do I, such that I is invertible. Zero, of course, is not. And when you take the invertible ideals modulo of principal ideals, this kind of cuts out the noise of all these crazy invertible ideals floating around, and you get what's called a class group. So a couple of observations. The cool thing about Dedekind domains is every non-zero ideal is invertible, so the playground is everything, right? Notice, when is this trivial? This is trivial precisely when every invertible ideal happens to be principal. So for a Dedekind domain, that means every ideal is principal.
Oh, that should be XR, right? And principal.
Oh, yes, you're absolutely right. That's right. So let me give you the following here. So here's some kind of new stuff about Dedekind. Some of this I've mentioned in passing, but I'll tie it together here. 5.3.4, let R be Dedekind. So this is basically a list of a few properties that Dedekind domains enjoy. One, R is a UFD, and only R is a PID. Two, if R has only finitely many maximal ideals, then R is a principal ideal domain. Three, every ideal of R can be generated by no more than two elements. And in fact, Dedekind domains are said to have 1.5 generator properties. What in the world does that mean? That means that basically, well, for Dedekind domain, there's more general research that's done on when and how to generate property. But in the realm of Dedekind domains, what that means is you can put on a blindfold and pull out any non-zero element of that Dedekind domain. And that can be one of the two generators. The other one you have to choose a little bit more carefully, and we'll see that in the proof actually. So it's not just two generators will suffice. You can pick essentially one of them, you can pick at random. Okay, so let's go through some of this. Number one,
It's one dimensional.
right. This is always, right? And if R is Dedekind, it is one dimensional. And one dimensional plus UFD equal to PID. We've already shown that. Okay, number two depends on something that I sort of showed in class and challenged you to do the more general case. Maybe I should actually do that. I think that might be my short homework. Well, something that we've done earlier makes this a little bit easier. Anybody tell me what it is? Yeah.
R is semi-quasi-local and I is invertible, then I is principal.
Okay, yeah, that's exactly what we want. It suffices. Actually, I don't need to do the primes. In fact, I'll take your lead on that one. And since R is Dedekind, I is vertical, right? And that's key, you have key there, and that is, but we don't just know it's, Dedekind, we now know that it's semilocal. Right, because one of our results is if you have an invertible ideal of a semi-local domain, actually even semi-quasi-local, then it's principal, right? So there we go, every ideal. How about this one? Every ideal can be generated by at most two elements.
Well, we haven't proved Kroll's height theorem yet, so. I guess we can't use that.
Well, what we can use, actually, essentially what this is Chinese remember. What does Macaulay call it?
Sun Tzu or something.
Okay, I should probably learn who it was in China that has the theory. So, here we will assume, in my notation here, all primes distinct. And EI is greater than or equal to 1. Okay, so if I write two different PI and PJ. Okay, and of course, I want all the EIs to be greater than or equal to 1, otherwise I wouldn't have written the stupid thing in the first place. Alright. Now I gotta generate this with two elements, and in fact, my proof is gonna show the 1.5 thing I claim. Here's what I'm gonna do. I'm gonna pick any. Pick any non-zero element that I want. And now think of this element as generating an ideal. Now, what do I know about this? Well, I don't know much, but I know it's contained in I. Right. So,
That's the function of the VA.
and then maybe you've got some others going on with it too. And what did I call those? And just like in my notation here above, these QIs are prime ideals. They're all distinct and they're different from the PIs because otherwise I just do this. And what can you say about the FIs? Greater than or perhaps equal to EI because of this containment. Everybody agree with that? Now, the idea, I can already generate this with one element if I'm so freaking lucky that all these FIs turned out to be EIs. And there were no trail, and all the AIs turned out to be 0. Let me make that AI 0. If these all turned out to be 0, and all these turned out to be EIs, look at me, I've already generated it, right? So I need to find another generator that kind of shades. See, I've got too much stuff, right? This is like, this is what I'm trying to build. This is the Statue of David. This is the rock it's in. I've got to come with my chisel and chisel this down to this and get rid of all the Q's and perhaps some of the P's. Agree? So how do I go about doing that? Well, the first thing I'm going to do is I'm going to chisel off the extra P's that I need in the following sense. I'm going to select B in R such that B is in EI, but not in PI, EVI plus 1. Now, question, how can I do this? I'm gonna pick some magic BNR. I claim I can do this, where B is contained in each PI, but not each PI to the EI, but not in the next power of PI. Do this locally, and I'm going to do that first, right? First, right? So what I'm going to do is I'm just going to take these primes. I'm going to take the set theoretic union, take its complement, I'm going to localize it. Our localized at S is again Dedekind, but more than that, it is what? PID. And this follows from previous theorem number 2, or this theorem number 2, right? Because now you have a Dedekind domain that has only finitely many primes. So left. So each one of these is generated by some element. I'm going to call it I. Now that I'm up here, can you give me a prescription for finding such a B.
I is the EI.
There you go. That fits each of these precisely, and B is precisely in the I power of PI, because it's just, it's, not the I, the EI power of PI, because it's exactly the right power, it doesn't go too far, right? Everybody agree with that? Unfortunately, that's in the localization. Right, and I wanted it to be in all, what can I do? Just clear the denominators. Uh, because actually, this is the form B over S, for some S in here, but this S misses all these primes, right? So if I clear it out to get it down here, B has to miss all those primes as well, and so I don't interfere with the exponent I've got. Is everybody okay with that? Okie dokie so far. So what have I got now? So now I've got this B. And it's in, well, it's certainly an I, isn't it? Right? Because it's in PIDI and so forth. So whatever this thing is, it's in there. And the B is basically used to kind of shave this off. But this isn't quite good because, of course, to get this B by multiplying by S, right? Multiply by S to get this thing down the ring. This is, there's a lot of other stuff that can come in here because S down in the global ring R, you might have lots of like prime ideals dividing, right?
Can't we do the same thing with Q's?
Well, right, but so how do we get around this here? What we want to do, I think, is now uh wait. Or anybody want to take a guess what I want to do here?
Oh,
This is kind of a little chatty familiar theorem, kind of trick going on here. Right. So, now, what do I know about X? Well, let me go ahead and write this down here. Um, so I don't know much, but I can factor, and here I'll have, first claim is that BI is equal to EI. Everybody okay? Well, certainly we want the veracity of this claim to be true, because then we'll have this where we want it, right? Why is this true? Well, what's it? Perhaps some other prime ideals,
Okay.
right? There perhaps other prime ideals. Notice that X minus B is in PI plus one. Because this is how, by the way, we can find such a solution, right? This is, I really do gloss over that, I apologize. Why can we find a solution? Because this is a system of what, K plus T equations. That's right, that's right. I've assumed that all these primes are distinct, so the PIs are all co-maximal, right? And so the powers of the PI are co-maximal. And so this is the Chine-Tremaine theorem. This is a straight up application of Chine-Tremaine. So, okay, we have found this X, we factor X, we consider X as an ideal and factor it into this private primes. Now I claim that the PI exponent on the ideal factorization of X must match the one on, I, right? But recall that V, right. This certainly means that this is of course contained in PI, so this means that X is in PI. PI, agree? Because this is in PI, I'm sorry, this is in B is in PI to the EI, this is in PI to the EI, right? And so X must be in there, right? But also, it can't be that. Can somebody explain that? Right. If this animal happens to be in PI to the EI plus one, and this is, that forces B to be in there, but it's not, right? So that was an important bit of this. So I can update this. Now, because because of this choice right here, you can actually show that the DIs and the QIs are distinct, because of this choice made. This choice right here. For example, if any QI contains one DI, then that means that X is messed up with regard to this, so forth, right? So if you look, so let's consider the ideal generated by A, my initial one, and X. This is P1, E1. No, it's not. It's P1, F1. PKFA. P1, A1. Plus, E1, E1, PK, EK. And notice each of these EIs are less than or equal to F. There's no maximal ideal that contains what I've got in square brackets because of the fact these are all the same, right? Because if this lived inside any prime ideal, then it would have to, the prime ideal would have to contain one of the DIs and one of either the PIs or the QIs, which is impossible. So this is and there you go. So I can generate this thing by the two elements, A and X. So it's two generated. And notice that the proof showed we can actually get it in 1.5 generators because I essentially picked A, as long as I avoid 0, I picked it at random. Okay. Okay. Got more of this stuff to explore next time. Any questions? All right. If not, I will see you folks on Wednesday.